Alright, this is the same setup as before with respect to the MOSFET there. I think you can see that, or I don't know, maybe you can't see. Maybe, but I'm going to show you anyway, okay? There's the IRF PG50 MOSFET. There's the gate pin of the MOSFET with a yellow wire that goes to the negative pole of this 12-volt battery. You see that? There's nothing else connected to the gate of the MOSFET. At the negative pole of the battery, I also have connected the positive pole of this little 3 AA battery stack here. I took 3 AA batteries and put them in a piece of heat shrink tubing and then shrunk that tube down. So there's a 4.5 volt battery stack there. Those are 3 AA batteries, okay? That's a 12 volt battery. The gate of the MOSFET is connected to the negative pole of the 12 volt battery, right? This is the negative bias battery, right? Now I have a bulb, a light bulb in there. The drain, red wire goes through the light bulb. I'm going to get this out of the way for now. The red wire goes through the light bulb to the drain of the MOSFET. The only thing connected to the source of the MOSFET right now is the reference lead of this oscilloscope probe. I've put the probe there now just because I'm going to be using it in a few minutes and I don't want to be fumbling around hooking it up. But I think you can see, can you see? Gate, drain, source. There's nothing connected to the source pin right now, right? You see that? Alright. Now what I'm going to do is I'm going to take another jumper lead and I'm also going to connect that to the source pin. If I can see it like that. Okay? Oops, it fell off. Cheap Chinese alligator junk. Alright. Now let's make sure that that little jumper is not shorting to the drain pin of the MOSFET. Alright? Come on, focus. Okay, in fact, let's just go ahead and hook it up over here like that. Okay, so can you see that that is not shorting to the drain pin of the MOSFET? I hope so. Alright, now 4.5 volts negative bias battery. This will lower the source voltage to below the voltage at the gate. Is the light bulb coming on? Is that showing up on the video or not? Is it? Is it? Is that showing up or not? Huh? Okay, now I have the oscilloscope over there. It's really too bad that I can't get all of this in the view at the same time. But I have the oscilloscope over there connected to that oscilloscope probe. And it right now is actually at 50 volts per division with the 10x attenuated probe. Okay? You see that? Can you see that that is in fact the scope probe lead that is connected to the MOSFET drain? I think you can. Okay? Right? Now, when I make that same contact, I'm going to do this. Okay? When I make that same contact, watch the oscilloscope trace. Barely moves at all, right? Oh, by the way, I have the scope's time base right now set at half a microsecond per division. Okay? That's 500 nanoseconds per division. Can you see that? See what happens when I try to use a tripod? Anyhow, there is the 500 nanosecond mark on the scope's time base. Okay, I hope that showed up. I cannot simultaneously see the monitor and what I'm looking at there with all of that. All right. 50 volts per division, remember that. Okay, so I've shown you here that with a light bulb in there and 12 volts on the battery, I can make the light bulb light just fine. Right? Right? Okay. Now for oscillations, this system will not oscillate for me with 12 volts, and it also won't oscillate with the nonlinear light bulb load in there. But I have here a 5 ohm power resistor. Can you see the label on there? It's a Dale, what is it? HL-20-02Z-5. This is a 20 watt, 5 ohm, 5% tolerance power resistor with a couple of wires soldered to it. So I'm going to take this and I'm going to put it in place of the nonlinear light bulb load, like that. Then I'm going to take the battery and turn it into a 24 volt battery, like that. Right? 24 volt battery, drain connected through the load, or rather positive pole of the battery through the load to the drain of the MOSFET where the scope probe is, from the gate of the MOSFET to the negative battery pole of the 24 volt battery stack. And you can see that I've made no other changes, right? Now I'm going to do the same thing again. This little guy, like that. Now watch the scope screen. Okay, here we go. Is it oscillating or not? Is it oscillating at a high frequency because there's very little inductance in here, or not? Is this being faked or not? Huh? 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 Is it fake? Is that fake? That's at 50 volts per division. Alright, so I'm seeing 1, 2, 3, 4, almost 5 full divisions of oscillation amplitude there. This is between this is the drain trace of the MOSFET measured relative to the source pin of the MOSFET at 50 volts per division. Do you see those oscillations? Huh? Is it oscillating or not? Oh, there it didn't oscillate, you see? One, two, three, 4, 5, almost 6. 1, 2, 3, 4. No, almost 5 divisions there at 50 volts per division. So we have 250 volts just about right there. Okay? What's happening here? Huh? That's all I'm doing, is just that. Now, what would happen if I took a function generator and put it where this battery is instead? Huh? What do you think would happen? Huh? Well, why don't we find out? Oops, that's the scope probe lead, sorry. Where's the function generator? Here it is. There's a function generator lead. I wasn't actually going to do this, but I might as well. That's why I'm not prepared for it. So let's take the black output from the, or rather the red output from the FG, and hook it to that jumper that's connected to the source of the MOSFET. Let's take the black output from the function generator and hook it to the positive pole of the battery, or rather the negative pole of the battery, where the gate is also hooked up. Alright, you see that? Now I'm going to turn up the function generator amplitude, and I have the function generator set to make about a 1 Hertz oscillation. a 1 hertz interruption there, okay? Is it oscillating when the function generator turns on or not? Huh? 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 Am I faking this? Huh? If anybody thinks I'm faking this, I want you to repeat the demonstration yourself before you accuse me of fakery, okay? You put this together yourself, and then if you somehow fail to reproduce this, then you might be able to have a foot to stand on if you accuse me of faking. What part of this is so difficult to understand? Well, I know, and I know why it's difficult to understand. It's because Rosemary Ainsley is blinded by her thesis, and she is so ignorant that she can't even read or understand a reference. Common gate oscillator, common gate amplifier. Check the wiki. Thank you for watching.